Okay, now visible.
Hearty welcome to the third and final day of our National Virtual Conference on Emerging Trends in Applied Mathematics. Today, we are having the talk by Dr. Satyanath Pante sir, Professor and Head from the Department of Mathematics, NIT. Here, we have Dr. VGM, Assistant Professor from the Department of Mathematics, to welcome Dr. Pante sir. Over to you, dear Vijay.
Thank you, sister. Good evening, everyone, and welcome to the third day of National Webinar on Applied Mathematics. It's my pleasure to introduce today's speaker, Dr. Satyananda Panda, Professor and Head, Department of Mathematics, School of Natural Sciences, National Institute of Technology, Calicut. He will be delivering a lecture on surface decontamination, a mathematical model. He completed his master's and PhD in Technical University, Kaiserslautern, Germany. To his credit includes various international publications, authoring many books in the field of computational fluid mechanics, asymptotic analysis, mathematical modeling, numerical simulation, etc. With immense pleasure, I welcome you, Sir, Dr. Satyananda Panda, on behalf of Department of Mathematics, St. Thomas College, Thrissur, and everyone gathered here. Also, I would like to welcome all the participants, looking forward for a great session. Thank you.
So, should I start? Hello?
Yes, sir. Over to you, sir.
Okay, thank you then. So, at the very beginning, I must say thanks to Sister Dr. Julie for inviting me for this seminar or that webinar on emerging trends in applied mathematics. It is really, we are so close. So, you are organizing in Thrissur and I am working in NIT Calicut, but I am happy to know that some of the faculty are working on fluid mechanics. And this webinar is one of the opportunity to know each other. And I'm extremely happy that the St. Thomas College Thrissur is organizing such a seminar, which is based on a current topics on research. So what I would like to now deliver in my talk is the current one topic is a surface decontamination. And I choose this may be a most relevant topic because, as you know, in Corona, the very, very important concept for all of us is that how to sanitize your hand. So this is now my surface and you have to decontaminate. So like you have a lot of now different type of this sanitizer. So many companies are now selling and you are buying, and really are you cleaning, are you like decontaminating all the bacteria or any viruses that is close contact on the surface or on the hand or any other, maybe in your dining table, maybe on the floor. So many possibilities are there that we are always trying to decontaminate and using these chemical agents. So now the question is, it's very clear, might be all of you, that it is a question of the problem comes under a modeling on population. So like bacteria are the population here, and the question is how to model, so how to kill through the agent, or how many are growing actually. So this is the a topic for my talk. So the presentation outline, I have to first introduce what is a problem. And one problem, we are working from a company which is a clay-based product for green cleansing. So basically, there are many sanitizers. And this is one product, it is purely from the soil. So a very natural, a green product. So this is and how you can use it for your cleansing purposes. Then how mathematically you can model such a phenomena like how bacteria is killing and how you are actually disinfecting. Then what is the purpose? Now then we'll go for the solution procedure, and then finally I will conclude my talk. So this problem is a company which is called a clay MIFF product. So this company is based in many in Arabian countries, and they have this type of like a cosmetic stuffs like a soap, the hand clay wash. So this is one of the product is like a tayammum pack. So like if you go to in a many Gulf country, they have their own sanitizers, and basically it's a product of the very natural contents. Like so, it is a soil. So they dig actually close to 10 meters, and they take the very refined one and put this water, and then they prepare it. So it is a very natural antiseptic product. And this is one example, but the modeling is not based on that particularly this product, but it is based on a very general, you have now chemical agent, and you have the surface, and you have the bacteria. So these three interaction, how you can model or how to describe mathematically. So that is the main idea. So as you know, in this particular product, we have clay formation. So how we will do this? This raw clay, this company is collecting. And so they dig minimum 10 feet underground. And then you have to pre-process it before going to in a powder form. So once it is pre-processed, then you have to add a very refined or RO water, and then it is ready for the cleansing purposes. So who are using this? You know, in many in a Gulf countries, a lot of like these industries, and most probably this civil aviation industry, like a lot of people, those who are traveling, they are using this type of products. So the company asked us that how to optimize means how much product you need in order to decontaminate. So that was one of the mathematical topic for us. So the basic idea, as all of you know, like we have the mixed clay product, and then we have to like mix it, and then you have to put in a tank, then you in the spray tank, and then you have to water jet that has to come out. And then you have to spray on the surface where you want to clean. And then you have to rub it, rinse the surface with water. And finally, you check whether it's clean or not, or still bacteria are there or not. So the industrial objective is to how much now, as you know, frequently we are using many sanitizing products. So like I have one, as you see now, this is one Dettol product. And I'm frequently using now. So the question is how much this product I have to use. So that is one interesting question. So like it is a optimization. So how much you need that chemical agent so that entire you can clean your surface. So let us take one example. Mathematics means if you do some mathematics, you also need a supporting experimental stuff. So this is one experimental that is now undergoing at the biotechnology lab. So you have now this bacteria, and which is called like a simple one, Escherichia coli. So that is in short form we say E. coli. So you have bacteria at one hand. You have now this clay product, the simple one, and you have to mix with water, and then you keep in a medical setup, and then you check now with a certain temperature. So once you mix this chemical agent, so from the day one onwards, like as you can see in the left hand side. So the clay concentration, if it is 0%, so nothing is mixed, then definitely your viruses or bacteria are very, very high. So then you go on 5% mixing. So then you go on 10%, you go on 15%, you go on 20%. So you keep on. Don't think that mixing more, like taking more like sanitized product, that doesn't mean that it will kill all your now the bacteria. So what is the efficiency then? So this is the idea now. And you know, this bacteria, the population, we can measure like a number, means like a bacterias are CFU, like a colony formation unit. So initially, you look, you have 19 into 10 power 6, so huge numbers of bacteria. And their production rate is very, very high. So taking into account now with this effect, how you will now describe mathematically. So look the data, how it is now. What is the growth now, this bacteria? So once you have 0% clay concentration, that means your hand is dirty now. And you are not mixing anything, any chemical agent. So basically you are not killing the bacteria. So at the very initial time, this is TNTC, means it is a scientific term, too numerous to count. So like a infinity now. So then in day 1, day 2, day 3, it has nothing to die. So it is same now, you can see now. So always there is a risk of contamination. So then now you can go for a 5%. So after a long time, you see at day 3, you have 165 into 10. So like a lot of bacteria you have killed in between. So like if you are mixing 10%, then obviously it has the effective is very high. Now you can see, observe. So in the day 1 itself now, so reducing. And then 15% you see now is very similar, but it is not exact. So then again in the 20%, so at the initial hour, you have huge bacteria, but then slowly these are decaying. So then when you have mathematical model, because if you write like TNTC and all, then computer will not accept. So then like you have to define how big this TNTC. Now then at 0%, let's say I told you in the beginning, so the colony formation unit of the bacteria is 0 hours, is very high. So like 10 power 6. And then in the day 1, it is increasing now, you see rapidly now. So you look now how this population, maybe corona or maybe the viruses or in the bacteria, how the rate of growing you see, if you are not killing this. So if there is no preventive measures now, then they are rapidly growing and it is dangerous for us now. But once you have something, so like any chemical agents or you have medicines, so like you see how they are decaying. But the question is, really now, whether all medicine, all sanitizing product, are they effective? Are they able to kill the bacteria now? So now the question, we start from a simple. So what is a mathematical modeling now? A modeling has to be in such a way that if you not have much idea, then start from a very simple model and make as complex as possible. So in my case now, let us start with a very simple ordinary differential equation that all of you are studying in your college, maybe in the BSc course, differential equation. So this model now, like a B is my bacteria. So total bacteria or the population present on the surface at time t is equal to 0, we have B naught. And then we have clay concentration because it is a mixing now. So now my only thing is that I put some clay, so some chemical, and I say that this chemical property is same for all the time. And then I have to see how my populations are growing or decaying. So I have, you see now alpha time B, so this is an increasing factor, so growing in this way. So alpha is a growth rate. And lambda is now effective density, so it's a quadratic effect. So the population has to decay. And because you are now C in this model is there, so because you are now giving some concentration, so chemical concentration is there, so bacteria has to decay. So we have minus sign here. So this is a very simple ordinary differential equation, a population model, basically a quadratic one. But now always in this population model or in the ordinary differential equation, even if corona model also, if you coronavirus, if you model this population, you have a lot of this type of model, please remember. But the question is how to compute now this alpha, lambda, and beta. So the population, the modeling parameter, the exact computation is always a difficult job. So because we have data now here, and then we have computed now, we have like a, this is always an interesting mathematical model problem, that how to identify the parameters. So it is called an optimization problem. So like we saw in this problem that suppose the alpha and C is constant, and suppose you neglect the concentration. So you just check how bacteria is growing or decaying without any chemical agent. Then based on the data, we observe that now alpha is 2 point something here, and lambda, the quadratic term, is very small. That means the quadratic effect, the nonlinear effect, is no need to now take into account in your model. So that means when you are doing a modeling of anything, please don't think that by writing a very, very big term in your equation, and don't think that people will be happy or you are doing a wonderful or very extraordinary works. That is not correct. You look now whether this parameter is feasible for your model. If it is not, you throw it. So like we have analyzed here that how big or how small my two parameters. So alpha is quite big, so it is 2 point, and lambda is very, very small. So the quadratic effect is negligible. So I don't need, so I have to safely now remove the quadratic effect. That means the bacteria is not dying, or coronaviruses maybe not dying on its own. So that means you need a chemical effect, or they have to grow always. So that is the question. Maybe, in a corona effect, many people were thinking that India or many Asian countries, our geography is very, very different. We have maybe like a hot temperature, we have cold effect, and people were thinking that the corona in the hot, maybe in April or May, it will die and India will be not so much affected. But it is not true. So because they are independent of the now temperature, the effect of temperature. So now you have now you exclude the quadratic effect in your model, and just you have a very simple one. So the population is just, it is growing or it is decaying. So only on two factor, one is a growth factor, alpha, and another is a beta, which is coming from your sanitizers or the chemical effect. So now, as you know, this is a very simple ordinary differential equation. If C is given, you can solve within a minute. And now if I know my alpha, and if I know my beta parameter, so beta I have computed. This is an optimization problem because I have the given data based on the experimental data from the biotechnology lab. I see if I add 5% chemical effect, or if my concentration effect is 10%, then you see my beta, the scaling effect is 5% is very big now here. So that means the more the chemical concentration, the smaller the beta. So it may be a good, that means beta has to be a small in this case. So that means now this is one example. Now beta has to decay with the C. So this is a relation between the chemical, the agent, and your mathematical parameters inside the model. So now this is an initial value problem, and I know my initial conditions. So then exact solution is this one, just it is ordinary differential equation, and you can solve it. So then if you plot now these two solutions, because it is decaying phenomena. So one is a model now, this blue one, and the dot, this the red star, they are the experimental data now. So you see, these are the two things. One is at 5% concentration, what is the difference in my model? And if I take the 15%, you see it's very big difference now. So in a 5%, I'm very close. So 5% maybe it is the chemical is not capable to kill all the bacteria. So maybe I am having the very quite simple result. But if I am increasing now, then effect is not same. And then a lot of errors I had. So, always in a mathematical modeling, it is always interesting that how much if you compare with your industrial data, then what is the error you are computing in your modeling and how can you decrease it? This is always the problem and the challenge for the researchers. So because I am not satisfied with my model because I have here error, so then I have to look for some other possibility. So then here I have two things. It is now a coupling effect. So one is a population that has to decay, one has to grow with alpha, and it has to also decay with C. So once your chemical is now you are mixing on, then on the surface, the bacteria has to decay. But another interesting is that this all chemicals, like how many hours it will work, let's say. So after maybe 1 hour, after maybe 5 minutes, after maybe 20 minutes, the effect has to go, it has to diffuse. It will not work anymore. So now this chemical, the quality, which brands now, that matters. So the chemical also has to decay with respect to time, and the population bacteria has to also decay with time. So now I have the coupling effect here. But in this coupling effect, now the ODE, ordinary differential equation, you can set off. Let's say in the time effect, both are maybe, then you can write in the differential equation in this form, dB over dC. You can make a simple simplification and you can write in this way. And then finally, I can solve NAD by hand only. I don't need a lot of computational stuff or anything. So my bacteria, which is depending on chemical concentration, is nothing but minus alpha log of C plus beta time the chemical concentration plus a constant. And because you have initial condition, you can compute all these things. So, and the given data will help you to find the alpha and beta. And this concentration is now from 0 to 20. So now, if I look my result, you have now 3 days now, day 1, day 2, and day 3. So now, so if I look from day 1, let's say day 1 is the green one. So if I look now, day 1, you see now, starting is close to now 1,600, but the decreasing rate is not so good now because at different now you see at different chemical concentration because you're starting chemical concentration and all. So in the day 1 now, it has to be like one can expect like quickly nothing, the bacteria has to decay. But in the similarly, day 2 is quite better and day 3 is decaying faster. And when you have like 20%, you see now very quick now. So the decay rate is very fast now. So this is a relation. There is no time effect, but it is a relation between a population and the chemical concentration. So time is independent of the solution. So we have now the final. Now if I plot now ODE solution, then I have already now computed my beta, that is the model parameter, so decaying effect. Then I have C, one is a simulation and another is a experimental. So the red curve is experimental one and another is a simulation one. So the error is very high. So my model is, I can say, it's not a good one. And I have to look something, maybe a different one, where bacteria has to also depend on the species. So the species is like, in a corona might be all of you might have experiencing. Not that every patient, those who are tested positive are dying. It is not true because that immune power is also very, very high. So now the question is, let's say you have a surface and let's say maybe surface is maybe on table, maybe a meat product, maybe any fruit, maybe any sweet product. So any type of surfaces you can use now and leave the bacteria now, how it will grow. I hope if you take two things, one is just a wood and another is, let's say, a fruit, maybe apple or anything you can keep it. Then definitely when on a wood, bacteria are nothing to get and it may automatically die. So people are telling now, as you know, if you read a newspaper, the newspaper has not much effect like a transmission if the corona may not enter through that because there is no food and it may die. So similarly now in the mathematical modeling also, if we want to complicate it, the process, So now we have here two things. This is now a PDE modeling. So we have to understand what is a partial differential equation. And the partial differential equation is different from the ordinary differential equation is that the partial differential equation depends on many independent parameters. So many independent parameters means always we have now one parameter we have taken from the ordinary differential equation model. So time has to be there. And now another is now my space. So look, suppose you have kept a meat product, suppose. Okay, so a good one you have kept in a dining table, and then you thought, okay, after 5 hours I will take the food. So within this 5 hours, like let's say this is your container. So don't confuse it too much. So this bottom one is actually a surface of your container. So I have kept in other ways actually. So now that means the bacteria population are very high on the surface. This is called the bacteria region. And let's say you have also infectant. So you have kept now this chemical agent on the below. And then when bacteria wants to enter the next surface, so that means I have divided the region here. So one is on a surface, and little space I thought that many bacteria are highly populated part on a surface, so that delta is a very small. Then now another now on a surface, so what is the length now, total domain where you are now computing your bacteria? So let's say H is my total length, and then bacteria is free. So one condition I have taken like bottom is impermeable, means like if you down it or if you off it, now bacteria should not go away from like a free surface. So from the surface only it start to enter the below now. So that means below you have the full chemical agent, and once you enter that the delta region, once it is here and wants to enter in the next region, then you have to kill, your chemical has to kill. So that's written here that at the initial time t is equal to 0, the given bacteria are located at the surface, and with the advancement of time, the bacteria move upward from lower region to higher region. And it is assumed that the bacteria diffuses into the disinfectant solution. So because it is a disinfectants are there, it has to diffuse, means the bacteria has to, means the solution has to kill, and you will have the less number of bacteria. So now the question is, how mathematically you can now project such a problem or describe now. So mathematically now I have defined with a reaction diffusion model. Maybe all of you in your many BSc or MSc courses, I think I can say you have a heat equation, you have concentration equations, and it is very similar, you can see now. So heat equation is also one time partial derivative and then double derivative of space, and then heat has to diffuse, and this part is just a reaction. So if you have any extra now, because in our problem we have chemical effect and B is a bacteria, then this theta hat is just nothing, but it is coming from the chemical agent. So because there is a reaction on the surface, so now you have to decide whether the bacteria is dying or not. So whether it is diffusing or not. So we have, because it is a partial differential equation, so we have two things we have considered. One is a time space, and another is a length of your domain. So, but it always, you know, this in a mathematics, or if you are interested to the modeling side, I know in many mathematical PhD topic, if you defined a simply mathematical modeling which describe a boundary condition, then also many people have been awarded PhD degree. Even how small, it does not matter. But mathematically, how can you define? And maybe many of you, if you are the participants are many are students, then I have to give one message that anything in this world is changing only through the surfaces. Because, you know, as all of you know, we are using the marks because we are protecting two things from that. One is nose, because we have boundary. It has hole, the nostril, and we have mouth. Anything can enter through this. So because these two things we can accept, so they are the now my free surface, or they are the boundary for me. So once I am closing, so that means I am preventing the other agent not to enter to my body. So they are what I have to prescribe. So on this surface, so you know on the bottom surface, my bacteria are full. So let us take one ice cream now, a cone, ice cream cone. On the very top, that one you have to put on your tongue now. So on the very top of your ice cream cone, how bacteria are behaving. So the population is now another boundary condition. So the bacteria has to diffuse. Also, it has to interfere with the chemical agent. Then at the boundary, at the initial condition, also at the surface. So this beta, which is the bacteria now. So at the beta is another, like it is also a bacteria, but B hat is also a bacteria, but it is in the domain I have defined. But beta is also a bacteria, but I have defined on the surfaces. But they are the same, and then I have to couple it. Then finally on the free surface, that means when the entire at the end of your domain, you thought that bacteria has already all bacteria are killed. So that means nothing is there. And then the flux, you know, the derivative condition are the gradient, they are the changing things, whether any population or anything is changing. And this changing is a matter now, and in physics we call the flux. So that is almost zero now. And the initial condition, you have the bacteria within the domain of 0 to delta, you have full bacteria, and once it comes to the next domain, then you have 0 initially. Then the bacteria wants to cross the second domain and it has to kill. So we have now a very nice effect. So theta hat is now this theta hat is a killing effect. And K, now you know this K, you look here carefully, beta T is equal to delta times, delta is my thickness of your first domain, where a lot of, it is populated one, and this K is how much bacteria likes the surface. So if your surface is now, let's say a window pan, then what bacteria will do there? So it has to die, it's no food. So that means this K is small. But now for corona, for our cases now, this K is maybe my nose, the sensitivity of my nose, and how it is now, how bacteria are now staying there. So here this K has to be defined. So it differs person to person, surface to surfaces. So that in the modeling, these are the stuff we have to take care. So that means not every surfaces are equal. Bacteria should not survive in the same rate for every surfaces. And that's why you need an additional effect, which is K, and this K will decide how much this bacteria like of the surfaces. So this is the model now, and you see now, this is the graphical interpretation. So these are all bacteria you can see now here very clearly. And many bacteria are in the film zone where it start now formation. And then what bacteria is doing, bacteria wants to enter into D4. But in D4, I have already chemical already set up. So once it crosses the delta region, then the bacteria has to diffuse because the chemical has to kill. But you see in the second region, many, so like some bacteria are also freely moving. That means your chemical agent, which company you are buying, may be not appropriate. So the bacteria has to sneak. So this is the idea or the graphical representation of your problem. Now, how to solve mathematically such a model? Maybe if any of your students now you are interested for research in future, you know, there is a very interesting problem, let me tell you, like aerodynamics. So maybe your coordinator, Dr. Julie, has a lot of idea maybe on the drag, and in the Anjali Devi, maybe she is expert in this area. So the question always, when you have this mathematical equations. The question is, this equation you are defined on a how big on a domain? Let's say from Calicut to Kannur I am interested. Suppose I am finding now my corona model. So corona model now, you know, all populations model now you have a data one from specific. Like always we say how many people are affected in Kozhikode districts, how many are affected in a Kannur districts, in a Malappuram districts. So they are now different to different region now you have. So suppose this corona phenomena, if you want to study, let's say, let me start from NIT Calicut and I want to reach up to Kannur. So up to Kannur, this distance I have to take, or I have to study from here to Calicut only city. So you see, this problem is now, it's not a fixed problem now, because your domain is now arbitrary. So in mathematics, one interesting concept is that you have to non-dimensionalize. So the non-dimensionalized concept is that you don't take any quantity which has dimension, like a force as a Newton's, maybe diffusivity as another like a unit. So this all unit, you don't take into consideration, you keep it aside, and you look your model which is independent now. So just it is a partial differential equation, and you don't care now what effect, what is the unit, whether it is kilogram, whether it is like any other stuff. We are not interested. We are just interested for a length, which is a non-dimensional also. Time is non-dimensional, and just you solve and you see the effect. But I am very much now like to highlight one thing. Maybe like our coordinator, Dr. Julie, has a lot of research program on fluid mechanics. And always our life is also not simple, please remember. Now we are now non-dimensionalize this problem. So if I non-dimensionalize, then I also get some non-dimensional parameters. Like in a fluid mechanics, maybe the coordinator, your coordinator can explain. So if you non-dimensionalize, then many other effects like Reynolds number, Prandtl numbers, Eckert numbers, Biot numbers, maybe many other. They are the bulk, they are the waste type of in this model, but they appear because if your dimension is lost, then you have to quantify the solution with respect to something. So this non-dimensional parameter has to now appear. And here theta is now my, as you see, one killing effect. And now if I have non-dimensionalized my everything, so again, let me say you. So if you look carefully now my model, then in this model now, population model, my B tilde is a population now. I have now everything's this non-dimensional quantity or tilde quantity. But, you know, in the heat equation, always suppose this theta appeared because I dimensionalize and then another quantity now appear here. But if something will appear in your model, then it is irritating because once you find a solution, maybe analytic or numerics, then always this type of quantity are appearing. And then your solution, even if it is analytic, then it is a bigger it will grow. So I thought, why this theta has to appear? It is simply a heat equation with a reaction effect. And we have boundary condition also with a non-dimensional and initial condition. So then I want to now have another idea, why this beta? Now you see in this equation, this theta I have removed. But if you want to remove this theta, then also again I have non-dimensionalized again. So they are all non-dimensional quantity, but again I have non-dimensionalized. Maybe you can note down and you can ask me in a question session why I am doing such type of things. The idea is if the model equation are free from any parameters, it is just an equation and you are solving. It is interesting, but you cannot do away with all this problem because I have removed here, but because I introduced root theta, now it appears in some other places because the world is conserved now. If something is happening here, let's say, if it is decreasing here, somewhere it has to increase because otherwise this conservation phenomena, it should not be, it has to prevail every time. So a decreasing phenomena, somewhere it has to increase. So that means I am looking for a comfort zone in my partial differential equation, but if I remove theta, then it is now entering in some other places. But okay, fine, because this is now my main equation, simply ordinary differential equation, partial differential equation, and I am comfortable, but these are all now things are appear in the boundary condition. So in my initial condition also, now you see root theta is even appearing. But this equation now is very nice to solve. It is a linear, but your initial and the boundary condition are a bit complicated. So now how to solve? So now I have another idea. If my entire domain is, let's say, always you have to look a lot of opportunity. We are understanding now, you know, Laplace transformation you are studying in your college or in your MSc syllabus. But this Laplace transform, just you are studying like where it is applicable. If it is problem is, let's say, a linear boundary condition or non-linear, then you are trying to now convert your PD to some other type of a simple algebraic equation, and you are computing that. So this is a transformation now. So I have now. So what I did now, I am looking now. Let's say my domain is very, very big, semi-analytic. So I consider from 0 to infinity. So if I consider 0 to infinity a very big domain, then how bacteria are flowing inside? So that means it is a semi-analytic domain, all you know, from 0 to infinity. But 0 to infinity is very difficult to solve. Let's say, but your length is a very big one. But this type of problem, many people are now trying to solve. Also, we can try Laplace transform method. Maybe Fourier series also there. So you see how mathematics is coming into picture. So you started something which you are describing for bacteria, but now many different things are coming now. But please you note also, those who are attending this talk, and I would like to tell you now, I am teaching this our NID, our mathematics, we have our own MSc student. And maybe we are getting very good students for our MSc program. But many students, when they come to project and all, they don't like partial differential equation, you know. And why they don't like, now I have the idea, the question is, many people are not good in calculus. So students, those who are attending, I request again and again, if you are interested for any things which are modeling or applicable mathematics, application oriented, without calculus, you cannot survive. And I also know that it is not your mistake. Maybe it is for me a small warning to also teachers or those who are participating here. We don't teach our calculus in a very nice way. A calculus is such a stuff that people has to see or feel it, what gradient is doing, what directional derivative are doing. So like in this case, now you see equation, I have partial differential equation, one is time, another is space, and it is reaction effect over which I have scaled it, and then I have the boundary conditions. So right here I can now apply my Laplace transform. But now we should also explain that where are these are applicable, Laplace transform, Fourier analysis. So now if I solve with a Laplace transform, I have analytic solution. And you know, analytic solution is exact instead of going for a many numerical solution. So this is one analytic solution I have at surface. So that means at surface, x is equal to 0 for all the time. So you just track on the surface how bacteria are growing. So that means you take your chemical sanitization and put on your palm, on the hand, and then you observe, don't now clean or whatever you like, then you observe how this population, bacteria population are dying or they are decaying or they are growing. So this is a one solution that will tell you everything. But now there are other many numerical methods also. Maybe in your colleges, maybe you have scope to learn finite difference. But here, let me tell you a little idea about finite volume. So what is difference in a finite volume? And then there are many numerical methods like a finite elements, finite volume, like a boundary elements, mesh-free methods, like a multigrids technique. So many huge numerical analysis are there. Now the numerical analysis itself is also huge and many people are doing research also. The question is how numerically you will find an algorithm to solve such a partial differential equation. So let me brief you what is now a finite volume method. So the finite volume method idea is that I am now, this is one volume, let's say at xi. So in a finite difference, you compute at xi. This is my domain length, and this is my now time domain, time growth. So at one point xi, now I compute my solution exactly. But finite volume is not like that. Your volume is now within a neighborhood of x minus half and xi plus half. So within this neighborhood now, you see the small dot lines. So they are one volume. So that means if you are solving any quantity like say population, space and time, so everywhere they are equal. So that is the average quantity now. So finite volume is a solution in the volume. But finite difference is solution at the point. So that is the difference. So maybe some of you might have the interesting question, then why many different type of techniques? The idea is that finite volumes is very exact when you have boundary conditions are like a Neumann boundary type or derivative boundary, because the finite volumes takes into account a weak form of your modeling. But finite difference is not. You have to forcefully discretize in the finite difference idea, means at the specific point only. So solution are depending on the position, but finite volume, the solution are depending on a volume. So if I solve now, so if I discretize now my model, so it is very simple now. So I have now at n plus 1, I am looking my solution. So I know the solution at my previous one n. So it is a explicit part. But you know this flux quantity. So bacteria fluxes. The fluxes means the bacteria are going from the one high, means one smaller region to the higher region. So higher region is less bacteria, please remember. So because the gradient is high. So in that case, we have the simple discretized equation, but it's just an idea of what is a finite volume method. We have implicitly discretized. So it is implicit discretization. And you have similarly the boundary condition discretization. So the question is how to solve, many, like if you are in this side, like a partial differential equation, I think only mathematics is not enough. You have to also know some technique like how to solve. So like numerically, like a code you have to prepare. Maybe C, maybe C++, maybe Fortran, maybe MATLAB, maybe CLab. So many are there. And students are nowadays very good in this area. So if you are very good in numerics, then when do you think for this line also, like how to develop or how to prepare a package for that. So now if I solve finally, so you see at different times, so the black one is my initial. So the black one means at the initial time, you see at x is equal to 0 on the surface, because it is non-dimensionalization, my bacteria population is 1, so very big. And immediately now, once I put the chemical agent, then bacteria suddenly now dying, many. You see now 0.6 close to all things on a surface, they are decaying. But after that, the decay is not so fast. They are exponentially decaying. So with respect to time, with this parameter, my lambda is equal to 1 and tau is equal to 1.5, I saw one phenomenon. That means in a corona cases also, if you have like exact now your medicine, they will die immediately many, but not all. Maybe like 40% are gone. But this 60% is your critical. So now in this second one, this is another simulation at the origin only. Only I am on the surface. So only on the surface I look. So with a chemical now, once you put the sanitization or any materials, so very fast it will decay, and after that you see very slow. So this is the tendency. But that means your chemical agent is effective, so it is decaying. But it is another idea now. You look now, bacteria is decaying, but after that sometimes also increasing. So this is one interesting now problem or have a very real application. In this corona cases, you might have observed many people after 2-3 days, they are getting better. or even the hospital are telling that the doctors, okay, fine, discharge, you go now. But after coming to home also, many people are again, they are succumbed to this disease, and it is difficult. There are many people are dying. So the reason, that this is one simple now is a results, but it is correct predicting. So that means if the agents are not so, chemical agents are not so effective one. So like I have in this parameter lambda is equal to 2 and tau is equal to 3. These are the killing effects. So like an industry has to say me exactly what is the lambda and tau. But then suddenly it is decreasing. But your now this chemical now this sanitizer is not any more effective. So that means the bacteria is growing, and this creates a problem or challenging to our health. So this a simple example that it indicates that the bacteria are not totally now eliminating. So they have the potential to grow, and this is one scenario. So that means if your product is not perfect, so the industry has to justify that if it is not up to that mark, then this type of phenomena we can observe. So I have to now conclude my things. So it is just a basic idea, but it is relevant in this case. And what I have told you that the surface decontamination problem, one problem, that means how mathematics is cleaning this world. So another one is how to model. So you can start with a simple ordinary differential equation, and that is a strategy always how to do a modeling. If you don't have a lot of idea, start a model which is as simple as possible and make it as complex also. So then you can extend it to partial differential equation. So then after that, you have to look for a solution procedure, and solution procedure is actually your mathematics involved. So one is a modeling involves your physics, your data science. So this is the things actually. And I have to tell you one thing, the future, all computers when we are buying, then, every computer, you can also look that a Core i5 now I am using, and it is written Intel. So that means Intel inside. So future also demands. When it is growing now, the data science, then everywhere this type of sticker will come, I think after some years, mathematics inside. So this mathematics now, how it is inside, now you see, we need a simple two example. One is a Laplace transform, and another is Fourier analysis. So this is deeper, you have to understand, and then you have to apply. And then another is a numeric side, like this is a finite volume idea I have explained you. So it is finite volume is difference from the finite difference. And maybe some of you have idea, finite difference. So, and then future work, like how we can optimize it. So how much, like, let's say that we are not talking here. So in an equation, we have to also include the optimization techniques. And then now I have open now questions. If you have anything, you can ask me. Otherwise, I have to say thanks once again to all of you. Thank you so for listening, and that's all from my side.
Any questions? You can write in the comments chat box, please. Sir, I have a question. Here,
Please.
sir, you are trying to do something with the COVID issue itself directly, isn't it so, sir?
It is madam, it is not a COVID, but it is another branch, like this is a sanitization I have to sanitize my surface.
Yes, sir.
I am looking for, it is corona is a bit sensitive actually, that is viruses, yes. And this model may not work for that, for coronavirus. You have to look for something different, but a very similar line you have to do.
Yes. So exactly.
So yes, this talk will give you a flavor that these are all population models. So corona population, the viruses are also one type of population, and how can you model it? So this is one idea for you.
So we can say that in a sense, mathematics can be used directly in an applied field in such a situation which is prevailing in our country, and
Oh,
the
yes.
scientists make use of that
Yes,
exactly.
yes. Yeah, you can. I think if some of you are interested, maybe look. Indian Institute of Science had one model, partial differential equation, and how it is working. Maybe if some of you are interested, you can have a look at it.
That was truly wonderful, sir, to hear you speak like that in such a prevailing situation, something which is very directly applicable. You can write any questions in the comment box if you wish, please. The participant sites.
But Sister Julie, I have one thing to request you.
Yes, sir.
We are receiving a lot of students from different parts of colleges because I am HOD, I am telling you. Otherwise, I have no doubts. Many parts of from Kerala, we are receiving students, but they are not good in calculus. Can you look into that?
Yes, we'll surely, sir. Because
Very
whenever
fundamental calculus is many students we are receiving, but they are not good. Even they have very poor idea about what is a line integral, what is a surface integral, what is a directional derivative, what is. So this part, please, if possible, give a rigorous training to them.
surely, sir, we will take care of that. For at least concerned about our college students, we can surely tell, sir. We'll take
Yes.
care of that because
And maybe I will let me share you one small example. Yesterday, I was very busy with conducting PhD interview. Maybe some of students from your college also might have attended. But out of 26 students, 25 students are interested for only one topic, graph theory only.
Okay, sir.
So, yeah, one topic only. We observe at the end that all people are interested to do research in one topic. But why it is happening? We have no problem to guide with many other topics, but people are not interested for other because they have fear in this calculus only. So modeling the differential equation, partial differential equation. So this type of things very fear now, many of your students maybe. So I request you to please create initiation or organize this type of talk, a modeling, differential equation, calculus, maybe very fundamental talks. And so students should get interest in this area. So I hope if you produce a little bit student interest in this area, I feel my talk will be much benefited, and I will be very happy that it was useful for me. So
Yes,
I'm representing not a speaker, just you have invited me as a speaker. I am not representing I am Satyanand Panda. I am representing from NID Calicut. And I want to speak to all the teachers are from here. If they are attending this conference, then please produce quality students. They are good in calculus. And this is one of the drawbacks, and many people are not interested to research in this line. So so I request you to divert. So other area also. So maybe like a differential equation, partial differential equation, optimization, numerical analysis, because many industry wants problem from this side only, and they can like this time some of students got placement only due to this area only, the applied mathematics. So applied mathematics is a now future for a lot, and I request all participants or faculty to have or to motivate the students.
Sure, sir. So, any questions? One more question. It has come in comment, and I'll read out the question, sir. Why did you, from Merlin Mary Abraham, one question has come. Why did you start with a quadratic effect for modeling the population?
Yeah, because many fundamental population model are you have a quadratic growth means like a decay. It's a population very fundamental model, I think, logistic population and all. Maybe if he or she has some idea, I described with a very fundamental model whether it has quadratic effect, because that is a logistic model. So I took that and then I wrote. But we saw in this case logistic model has no effect. So we stopped that. So we then, because the parameter, when we got a data from biotechnology department, we observed that this the second quadratic effect is negligible. Then we stop, and then we observe other parts. So that's the idea. Otherwise, nothing else actually.
Okay, sir. Any more questions? I think, sir, no one has pasted any questions in chat box.
Okay.
So,
Thank
thank you, sir. It is high time to render our vote of thanks to Dr. Satyananda Pandey, sir. Let me deliver the vote of thanks. Dear loving sir, Dr. Satyananda Pandey, sir, and all the participants, on behalf of St. Thomas College Organizing Committee of this international virtual conference, I render the gratitude from our heart for Dr. Satyananda Pandey, sir, for spending his valuable time to be here with us and giving a wonderful, excellent talk on the topic, which is very relevant for the times. Sir had explained how mathematics could be made applied into the direct life situations, especially regarding the COVID issue also, which is surely an eye-opener for all of the participants. Sir had told us a suggestion and also a compulsion in a sense for all the students who are belonging to mathematics streams and also to different applied mathematics streams to be thorough with the fundamental basic things of mathematics so that they could excel in life in later for future for the development of the nation. So rendering once more our immense gratitude for Dr. Pandey sir for accepting our invitation and spending his valuable time and expertise to share with in this national virtual conference webinar. We render the thanks from our heart and let me remain. Thank you, sir. Here we are officially concluding this National Virtual Conference, Emerging Trends in Applied Mathematics. So just before concluding, let me make a vote of thanks generally for all the 3 days from the beginning, inauguration, those who have worked for this to be a success days and nights previously from all of the people who were participating in the inauguration and for the invited speakers of 3 days, including the paper presentation sessions chaired by Dr. Paul Isaac, sir. Let me conclude with a note of thanks to the whole management and faculty of the St. Thomas College, especially of my department, mathematics department, who has done a lot for us to be conducting this national conference. Because of the technical side, I would like to thank Dr. HOD, Dr. Saju sir, who had made it possible, and also for the IQAC coordinators of the college. And especially I would like to thank my dear colleagues, assistant professors, Sir Ranjit Varghese and Sabu AS for their precious time and expertise in making this a live stream program. And also, let me thank all the paper presenters of the 2 days who have taken pains and presented the paper in the stipulated time and with excellence. And they have shared the ideas for the conferences to come in future. So making a note of thanks to all of you and to God Almighty, may I remind, thank you so much.
Okay then, sister, thank you.